Today is 10th of August 2020, so still we are talking about Fourier series. In the last lecture, we discussed some basic elements, definition of Fourier series, and different types of the intervals to be considered other than the standard 2π interval for a function to be discussed in the form of infinite geometric series. So we say that about the Fourier series, if you look into the yeah. So we see that yes, it has of great importance while talking about a series solution of certain functions. We should do follow certain criterions behind the scene. What are those criterions? One of the essential elements is that it should be periodic, and generally we consider the period of that periodic function as 2π. And then of course we can also look into the arbitrary period other than 2π, but the length should be like 2π. And also other than 2π, we can also have a different period, different from 2π. We will look into that today. So the theory of Fourier series is rather complicated, but when we look into the implementation, it is going to be pretty simple in comparison of the development, in comparison of the construction of the unknown coefficients that are going to be utilized to construct the series solution. On top of that, we say that Fourier series, in certain sense, so this series is more universal than Taylor series. Taylor series is the backbone of applied mathematics, yet we say that it is going to be more universal than that of Taylor series, because many discontinuous periodic functions of practical importance can be developed in Fourier series, but of course can't be done by utilizing Taylor series expansion. Before we discussed definition of Fourier series, we got an idea about the periodic function. A function is said to be periodic graphically if a certain portion of the graph is going to repeat itself over and over again. Mathematically, we say that for any positive constant p, if f of x plus p is equal to f of x, for any sort of value of x, we say that that function f of x, original function f of x, is said to be periodic with period p. Graphically, of course, we see certain portion of the graph is going to be repeated over and over again. Certain examples are there, like sine. Sine is a periodic function having period 2π. Not only 2π, you get the original function back at 4π, 6π, 8π, and then so on. The smallest period is going to be the fundamental period, or simply the period of that function. Constant function always going to be a periodic function, but there is no smallest possible value to be discussed as the fundamental period of a constant function, because when we talk about the graphical representation, constant function is going to be a straight line parallel to the line x-axis. So what is going to be the smallest possible portion of that line? There is no certain criterion behind this. And so we say that there is no fundamental period. While talking about the constant function, it is periodic. Whatever the period that you would like to take, you can take that portion of the graph. And then you see that since it's a straight line parallel to the line x-axis, so it is going to be repeated over and over again. Certain results are there very vital because once we develop those results, they could be utilized like an interval minus pi to pi for sine of kx for all sort of positive integral values of k is going to 0. No need to calculate this integral. Same is the case with cosine of kx. Combination of sine and cosine, combination of cosine with two different angles, combination of two sine with two different angles. So either take us to 0 or pi, depends upon the angle. If the angle is same, means m and n they are equal to each other, it will take us to pi, otherwise it is going to be 0. So no need to calculate over and over again. We can utilize these results. One of the very powerful result is there. For a periodic function with period 2 pi, we say that the interval from minus pi to pi could be replaced by an arbitrary period from c to c plus 2 pi, because c is going to be an arbitrary constant. So we have gone through with that. As a very special case, if c is equal to minus pi, for example, we will be having identical to the left hand side. If c is equal to 0, for example, so the interval is going to be from 0 to 2 pi. Length of the interval is same, but it could be changed. We can replace by an alternative interval with the same length, but different from minus pi to pi. We have gone through the proof of that. And then we discussed definition. What is Fourier series? We say that it is going to be infinite geometric series. All we need to calculate coefficients a0, which is going to be an element of an, and bn. So this series is going to be called as Fourier series or Fourier expression of f of x if the coefficients an and bn are given by. So we know the expression for an and bn. So for all sort of positive integral values of an is equal to this one and bn is equal to that one, where a0 is equal to this one. So it is basically an element of that one for n is equal to 0, for example. So you will be having cosine of 0 is 1 and you're left with that expression. So this is what we generally call the coefficients are going to be an and bn. So these coefficients given in equation number 7 are known as Euler-Fourier coefficients. So it means that we all need to calculate a0, we all need to calculate an, all we need to calculate bn. So once we calculate them, plug in over here and then expand them as much as you can. So we normally try to expand them with up to 3-4 non-zero terms so that we can observe a trend over there. It's a systematic arrangement. Geometric series, infinite geometric series, you will be having a systematic arrangement of those terms involving in that particular series. So this is how we normally try to expand this summation sign up to 3-4 non-zero terms so that to take an idea about the expression. So implementation, as we have seen at the start of this lecture, that theory is a bit complicated. I mean, if you are interested to calculate those unknown coefficients, how do we develop them? A bit demanding. But when we look into the implementation, pretty simple. All we need to calculate a0, an, and bn. Plug in over here, and you will be having a series. Formulas are there for a0, an, and bn. Change of interval. Yes, interval could be changed since f of x is periodic with period 2 pi. Cosine is also periodic. Sine is also periodic. So this combination, fx, cosine, nx, is also periodic with the same period 2 pi. Fx, sine nx is also going to be periodic with period 2 pi. So not only f of x, but all these combinations are going to be periodic of period 2 pi. So f of x is used in a knot. Fx cosine nx combination is used in an, and this combination is going to be utilized inside bn. So that integrand fx over here, this combination, that combination, they're all periodic with period 2 pi. So we say that yes, they could also be obtained equivalently from these expressions, where c is going to be an arbitrary constant. In a very special case, for example, if c is equal to minus pi. So if c is equal to minus pi, so these are the expressions you will obtain directly. An interval from minus pi to pi, minus pi to pi, minus pi to pi. Or if you take another value, like c is equal to 0, for example, then you will be having an interval from 0 to 2 pi, 0 to 2 pi, 0 to 2 pi. So the coefficients in this equation number 9 are useful in computing Fourier series if the generating function is defined over the interval from 0 to 2 pi. We took few examples to be solved in the last lecture. Find the Fourier series of the following functions which are periodic with period 2 pi. How do we observe the period? Since we have two types of representation of f of x, one is the geometrical representation, the graph, and the other one is mathematical formulation. So over here we see that it's a piecewise function. To take the first part, so it has two pieces. F of x is explicitly 0 over that particular part of the domain from minus pi to 0, and is 1 over a different part of the domain from 0 to pi. So how do we observe the period of f of x? Since it's a piecewise, two pieces are there, so you need to take the smallest and the largest value. So the largest value or the upper bound is going to be pi, the least value or the lower is going to be minus pi. So pi minus minus pi. So in this way, you will see that the length is going to be 2 pi. So it is periodic with period 2 pi. Just like if you want to take the length of a line, for example, you have 3 and then the extended line up to 5, for example. So how much is the length? 5 minus 3 is equal to 2 units. So same is the case, you see that in this case. So 2 pi minus 0, again, the length is going to be 2 pi. 3 pi by 2 minus the smallest value minus pi by 2. So again, it will take you 2 pi. So this is obviously that all these functions are periodic with period 2 pi. So we take one of the examples, like the first one, for example. It's a periodic function, period 2 pi. And if you are interested to see its geometry, because it's piecewise, it has two pieces over there. So we can look into the graph of f of x and its periodic extension. So it was given the value of f of x is 0 from minus pi to 0. So yes, it's there. And then from 0 to pi, it's 1. So this is all. We see that this is the portion of the graph which is going to be repeated over and over again. So this is our period from minus pi to pi. It's period. The length is 2 pi, extended from minus pi to pi. And that portion of the graph is going to be repeated. You see that? Again, repeated over and over again. So this portion of the graph is going to be repeated over and over again, known as the extension. Period is there, 0 and then 1 value, and then 0 and 1, 0 and 1, 0 and 1. So this is how we see geometry of the given function. Piecewise function, it's a 0 and then 1. Again, it will be 0 and 1, 0 and 1. All right. So Sorry for the interruption. All right, so we were talking about the geometry of this piecewise function. So it has two pieces. So one technical question is there, is it continuous? Let's look into the parts of the domain. X is greater than minus pi, less than 0. And then the next part is going to be started after 0 for any value of x greater than 0. So it means that 0 is not going to be included. At least at one place, there should be equality sign. Only then we consider 0. So we see that yes, there is a break in between minus pi and pi. So it is going to be discontinuous. From here, we can observe that. Anyway, we are interested to see the series solution, the infinite geometric representation of the series. So what we know, we all know about the formula corresponding to f of x. So it is going to be described in this equation number 10. All we need to calculate a naught, an, and bn. We have a formula for a naught, 1 upon pi extended from minus pi to pi f of x dx. Remember? But you see that we have two pieces. It's not a complete unit as one piece from minus pi to pi. It has been subdivided into two pieces over the part of the domain from minus pi to 0 and then from 0 to pi. So this is how we will split the interval from minus pi to pi into two pieces from minus pi to 0 and then from 0 to 1. So formula says that a naught is equal to an interval from minus pi to pi. So we split this one into two pieces. 1 upon pi sideways, minus pi to 0, and then from 0 to pi. So if you look into this portion of the domain, minus pi to 0, so what we see over that part of the domain, f of x is 0. And it is going to be 1 over that part of the domain. So minus pi to 0, f of x is 0. And from 0 to pi, f of x is 1. It is going to be vanished and we're left with that. Simplify that. Eventually we have a naught is equal to 1. Pretty much on the same line, we can calculate an. Again, we need to subdivide an interval from minus pi to pi with two pieces from minus pi to 0 and then from 0 to pi. Over that part of the domain, f of x is 0. 0 times anything is going to be 0. 1 over there, so we will left with 1 upon pi, 0 to pi, cosine nx dx. So it is going to be integrated cosine nx. So integral is going to be sine nx divided by n, and is taken outside. So if you apply the upper limit, sine n pi is going to be 0, sine of 0 is of course 0. So we see that an is going to be 0. We have calculated a naught as 1. Now an is equal to 0. Finally, we need to calculate bn. Same formula is there. Instead of cosine, it's sine nx split into two pieces, bring in 0 over the part from minus pi to 0 and then from 0 to pi 1. Simplified. So integral of sine is minus cosine. So on n, so taken outside. So cosine n pi minus cosine of 0. So negative sign is adjusted in such a way that you have 1 minus cosine n pi. Since we know that n is going to be positive integral value 1, 2, 3, 4. So we see that sine pi, 2 pi, 3 pi, 4 pi, and so on. So with alternative sign, we get the value of this expression cosine n pi. Could also be written as minus 1 raised to pi. So with alternative sign, when n is 1, it's negative. When n is 2, it is going to be positive. So we will be having 0. So Bn eventually is equal to this one. No, it all based upon the value. If you take the smallest value of n as 1, so B1 will be equal to 1 upon pi times 1 minus 1 raised to power 1 means minus 1, so plus 1. So we will left with 2 upon pi. For B, n is equal to 2, we will be having B2. So 1 upon 2 pi times 1 minus 1 raised to power 2 means it's positive 1. So 1 minus 1, 0. So B2 is going to be 0. Similarly, B3 for n is equal to 3 is going to be that one. B4 is 0, B5 is 0. So what can we expect about B6? It is also going to be 0. So it's very systematical. We have A0 and 0 for all sort of values of n. For different values of n, b's are there, b1, b2, b3, b4, b5. So plug in all these values in that equation number 10. A0 is 1, so eventually we will be having 1 by 2. So for all sort of values of n, so the first term is going to be vanished. B1 sine 1x. So B1, we have seen that it's 2 by pi. So 2 by pi times sine x. And then B2 is 0. B2 sine of 2x is 0. B3 is 2 by 3 pi sine 3x plus B4 is 0. And B5 is 2 by pi, 5 pi sine 5x and then so on. So we can also take 2 by pi common. So this is how we will be having this geometric series, infinite geometric series. It's very systematical, you see that? Sine of 1x upon 1, sine of 3x upon 3, sine of 5x upon 5. So you can guess the next term, very next term, sine of 7x upon 7. And this is what the trend is going to be there. We extend our journey as much as you can because the starting terms give you a pattern. So this is the solution. This is the series solution of the given periodic function with period 2. So pretty much on the same line, you can find the other two examples, second part and the third part. Only you need to split the interval. You have to see the interval. We can also see, yes, an alternative interval can also be utilized from 0 to 2 pi, as we have seen. Change of interval case is there. Yep, change of interval when c is equal to 0. So you will be having a formula for 0 to 2 pi, an 0 to 2 pi, and bn from 0 to 2 pi. For third part, it's from minus pi by 2 to 3 pi by 2. Again, the interval is going to be that one, so you need to extend it from minus pi by 2 to pi by 2, pi by 2 to 3, pi by 2. So this is how you move. No, the other way around. So we have been given the mathematical formulation. The expression was given in terms of pieces, and we discussed the geometrical aspect in the previous case. Now the other way around. Figure is given, the geometry is given. We need to find its Fourier series. Its periodic function, given that it's periodic, what the period is? 2 pi extended from minus pi to pi. So from minus pi to pi, we see that this is going to be the period. So in other words, that portion of the graph having more than one pieces is going to be repeated over and over again. It will be having one piece, minus pi to 0, then from 0 to pi by 2, pi by 2 to pi. So this is how, with these three pieces as one unit, this piecewise function is going to be repeated. Graphically, three pieces are going to be repeated over and over again. First of all 0, then 1, and then again 0. So with these three pieces, it is going to be repeated over and over again. So what the mathematical formulation? So f of x has got three pieces in this case. F of x would be 0 when x is greater than minus pi and less than 0. So this is the first part of the domain. And then f of x is equal to pi by 2 when x is greater than 0 and less than pi by 2. And then again, f of x is 0 when x is greater than pi, but less pi by 2, but less than pi. So this is how we will write it down in mathematical formulation. The expression of those three pieces. So 0, pi by 2, and then 0. 0, pi by 2, and then 0. If x is greater than minus pi and 0, then the second part of the domain was 0 to pi by 2, and third part pi by 2 to pi. So this is how we have written the expression, the pieces of the function f of x. Now what we need to do, all we need to calculate a naught, an and bn. This is the series. Formulas are there. A naught is there from minus pi to pi. The difference is that from the previous example, now minus pi to pi is to be splitted into three pieces, three intervals, minus pi to 0, 0 to pi by 2, and then from pi by 2 to pi. The corresponding values of the function are there, 0, pi by 2, and then 0. So this is how you will handle this. Think about that. So in the meanwhile, I generate a code. So it's 10th now progress. So we are interested to see present. We need the second option. Here is a preview. Sending, yes, it is fine. All right, so poll has been generated for you people to mark your attendance. All right, so we move forward. We have seen the previous example where the expression was given and we plotted the geometry and then the periodic extension over the period 2 pi. In this case, it's the alternative way, the other way around. Graph is given from the graphical representation from geometry. We write it down first, the expression. And then from the expression, we look into the Fourier series. The only thing that you need to take care about, you need to split the interval from minus pi to pi into 3 pieces, minus pi to 0, 0 to pi by 2, and then from pi by 2 to pi. So this is all. You have to calculate A naught, An, and B. As I said earlier, not necessarily that you need to talk about a period of 2 pi every time. So far that we have discussed different types of the functions, all of them were of period 2 pi. Whereas most functions and applications will have periods other than 2 pi. So what about those functions? Can we handle them? So the answer is yes, we can handle them. So we therefore obtain a Fourier series for a function f of x which is defined over the interval from minus L to L. No, if the interval is from minus L to L, the length of the interval would be L minus minus L means 2L. Just like from minus pi to pi, the length was 2 pi. So it is all. We will be having 2L. The period of that function, where L is going to be an arbitrary number, like minus 1 to 1, for example, minus 2 to 2, for example. So in this case, we will be having arbitrary period other than 2 pi. So we set as a trademark 2L, and then we will look into the value for L so that we can compute A naught, An, and Bn. So theorem states that the Fourier series of a function f of x which is periodic with period 2L and obtained over the interval from minus L to L is given by that expression. Pretty much the same expression is there. A naught upon 2 plus summation A n cosine n pi upon Lx plus Bn sine n pi upon Lx. So we have slightly different expression over here. If assume that L is equal to pi, for example, L is equal to pi, then pretty much the same identical expression. An cosine nx plus bn sine nx, pi upon pi will cancel, pi upon pi will cancel, and same is the case over here. Minus pi to pi, 1 upon pi, everything is identical. So other than pi, you are going to talk about L. In other words, just replace pi by L. So you will be having this expression. In this expression, if you replace L by pi, identical to the previous representation of the series. So anyway, it's not a new result, of course. I mean, it can be a deduction or can be an extended version of the previous infinite geometric series. We are not going to talk about the proof of this one, otherwise proof is available. We will take into consideration the implication. We will see the implementation of this Fourier series when the period is 2L over the interval from minus L to L. So A naught is there, An is there, and Bn is there. Only difference is there in the angle and the interval. So minus L to L, n pi upon Lx, n is going to be positive integral value. So as we have seen in the previous case, a change of interval is an option, even in that particular case. Since f of x in this case is periodic with period 2L, so same is the case with this combination. F of x cosine n pi upon Lx f of x sine n pi upon Lx, they are also going to be periodic with the same period as of the period of f of x, means 2L. Hence, the Fourier coefficients an and bn could be obtained equivalently from these expressions. C to c plus 2L. No, if you take c is equal to minus L, then this equation number 12, is pretty much the same as we have equation number 11, identical to each other. In case if you take c is equal to minus L. On top of that, if you take c is equal to 0, so then a naught would be 1 upon L 0 to 2L, an from 0 to 2L, and bn from 0 to 2L. So these coefficients in this equation number 13 are going to be useful in computing Fourier series if the genetic function is defined over the interval from 0 to 2L. So L is going to be an arbitrary number. So not only we restrict ourselves to take the interval from minus pi to pi or 0 to 2 pi, we could have numbers over there other than pi. As an example, you see it in this example, as you see. Find the Fourier series of the following functions. Again, piecewise functions are there. The first example, minus 1 is there over the interval from minus 1 to 0, and from 0 to 1, it is equal to 1. It has got two pieces over there, minus 1 and 1. What is the length of the interval? So 1 minus minus 1 is equal to 2, and we know the standard form of the period. It is going to be 2L. P is equal to 2L. And in this case, as a particular case, we see that P is equal to 1 minus minus 1 means 2. So P is equal to 2L is equal to 2. From here, you will calculate the value of L. L is going to be 1 in this case. So if L is equal to 1, you have every sort of formula. You see? If L is equal to 1, so 1 upon 1 minus 1 to 1, you need to calculate f of x. You need to calculate an, you need to calculate bn and plug in over here so that you can have a Fourier series. So formulas are there. L is equal to 1. First of all, replace the value of L as 1 everywhere in the formula. And then you look into the pieces. We have two pieces, minus 1 to 0, and then from 0 to 1. So it means that the interval from minus 1 to 1 to be split into two pieces, minus 1 to 0 and then from 0 to 1. So this is how you calculate A naught. A naught is to be calculated by utilizing two pieces of the interval with L is equal to 1. Alright, G. So I would ask you to try this example. Example number 1, part 1. Part 1 of this example. So I'm present here to see the outcome. Formulas are there. You try to see the outcome. We will discuss the outcome in the next few minutes. You try yourself. This is a standard notation. 2L is going to be a standard notation. Normally, your period will be from minus L to L. So what will be the length? L minus minus L to L. So this is all. It will be 2 times L. And the query from 115, my microphone and speakers